We're in Rosen, Discrete Mathematics and its Applications, section 5.4 on recursive algorithms. And here we are discussing how a recursive algorithm isn't always the most efficient way to go about tackling a problem or setting up your code. The Fibonacci numbers, as you know, are Fn, have the recursive formula Fn equals Fn minus 1 plus Fn minus 2. And that sets up the concept of a recursive algorithm for finding Fibonacci in. You would need two basis cases, and here is an example of a recursive algorithm for the Fibonacci numbers, where if you call n equal to 0, you're going to return 0, and if you call the algorithm with n equal 1, you're going to return a 1 as you would expect. If you call Fibonacci with an n greater than 1, this algorithm recursively calls itself at a value of n minus 1 and n minus 2, corresponding to the recursive definition. And eventually you get down to the basis cases, and the recursive algorithm will terminate. But let's count up the number of additions needed to find Fibonacci n using this recursive algorithm. So I'm going to be keeping, let's see if I can find where I was. So I'm going to be keeping track of this with, let me get back to red, with a number in parentheses is the number of additions for finding Fibonacci n. And for Fibonacci 0, that number is 0. And for Fibonacci 1, that number is 0 because those are my basis cases. There's no additions needed for those. But for Fibonacci 2, we see that we call for Fibonacci 1, which has 0, and Fibonacci 0, which has 0, but we have to add them together, so we get 1 addition for Fibonacci 2. How about Fibonacci 3? So Fibonacci 3, we're going to call Fibonacci 2, which has 1 addition, and we'll call Fibonacci 1, which has 0 additions, but we have to add it together, so we get 2 additions for Fibonacci 3. All right, so let's do a few more. Fibonacci 4 calls Fibonacci 3 with its 2 additions, and Fibonacci 2 with its 1 addition. We've got to add those together to get 4 additions for Fibonacci 4. Fibonacci 5 calls Fibonacci 4 with its 4 additions, and Fibonacci 3 with its 2 additions. We have to add those together, so we get 7 additions for Fibonacci 5. Now let's do one more. Fibonacci 6. It calls Fibonacci 5 with its 7 additions, and Fibonacci 4 with its 4 additions. We have to add those together, and so we get 12 additions to get Fibonacci 6. And perhaps by now you've noticed that these numbers are following a pattern. And the pattern is that these look a lot like the Fibonacci numbers minus 1. So Fibonacci 4 looks like Fibonacci 5 minus 1. Fibonacci 5, in terms of number of additions. So Fibonacci 5 requires 7 additions. Well, that's Fibonacci 6, which is 8, minus 1. And Fibonacci 6 requires 12 additions. Well, that's Fibonacci 7, which is 13, minus 1. And even up here, we'll do one more. Fibonacci 3 requires 2 additions. Well, that looks like Fibonacci 4, which is 3 minus 1. So, numbers of additions to find Fn, Fibonacci n, is Fibonacci n plus 1 minus 1. Now that's a conjecture. We can prove that by induction. I won't do that here. But what we can state, though, if that's true, and it certainly appears to be, and it is, then the recursive Fibonacci procedures, that implies the recursive Fibonacci procedure is big O of Fn plus 1. And we'll see in a later chapter that this is exponential growth. Okay, and exponential growth is generally not great for an algorithm. Let's take a look at another way that we could characterize the problem of finding Fibonacci n, and that is with what's known as an iterative algorithm. And here we have x equals 0 and x equals 1, single basis. If we return 0, then if we get a 0 in, then we return a 0. And we'll just add up the number necessary to get to Fibonacci n. So if 0 and 1 comes in, to get Fibonacci 1, we will add 0 and 1 and return that. We still get Fibonacci. We'll get Fibonacci 1 is equal to 1. For Fibonacci 2, we will also end up getting a 1 because Fibonacci 2 is I is 1 to 2. Let's see. F1 equals 1, F2 equals 1. So what happens here with 2? I equals 1, 2, n minus 1. So here we don't even start the loop with n equal 1 because it goes from I is 1 to n minus 1. So for I going 1 to 0, we'll just skip the loop and return y for that one. And for F2, we'll return 0 plus 1 to get F2. And in general, what happens is once we calculate F2, then x takes on the higher value, y takes on the z value we just added, and then we'll just continue that loop until we get up to whatever Fn we want. And since proc iterative Fibonacci has a single loop, of length n, then finding Fn has big O n, there's my addition right there, big O n complexity in terms of numbers of additions. So so even though a recursive algorithm might look extremely elegant, it is possible, if you're not careful, that you could be creating an algorithm that is more complex than needed. So that's something just to be careful about.